Hi, Bruce from Safari here, and we're going to give a presentation today on our new HiBlade lithium battery. We're going to show the actual EIS running in a simulator. It's so new that just having a look at a battery on the outside doesn't show you anything at all. And Casey, our development engineer, is going to step through that. Why are we doing this? Because on batteries today, you don't know that they failed until they failed, or until you've seen a lower voltage. You don't know why, you don't know what's going on, and you get you get very poor advance notice. In the EIS we're using, within the BMS, it can predict up to 15 failure modes with 4 resistances. And the tricky part is how you get a resistance from an impedance which has an imaginary level, and how do you get that with a battery running? This development that we've done here is together with NXP. We're a partner with them, and we actually run a sine wave through the battery every day and run a scan at 9 different frequency points through and take values of the resistance. Casey's going to show you that in action, and at the end of this we will show you the failure modes and the benefit of EIS to the end user.
Hi, I'm Casey. I'm a development engineer here at Safari working on the BMS with EIS enablement. Okay, this is the HiBlade, Quasar HiBlade battery, and today we're going to show how EIS works. So here is our battery management system measuring internal impedance of a battery cell in place with no laboratory equipment. The method is Electrochemical Impedance Spectroscopy, EIS. For this demonstration, instead of a real cell, we built a circuit that behaves electrically like one. That lets us make a single known change to it and check that the unit reports exactly that change and nothing else. The circuit has the same 3 electrical parts as a real cell has. A small series resistor plays the metal, the tabs, the welds, the current collectors. A large resistor plays the chemical reaction at the electrode surface. That's where the energy actually moves in and out. And a capacitor plays the charge layer that forms on the same surface. The unit's already measured this circuit once. That's the arc on the screen. Call that our healthy cell. Now I'm going to age this cell. Right now a second resistor sits in parallel with the reaction resistor. Think of the two as 2 patches of active electrode surface, both carrying the reaction. The switch disconnects one of them. That's what real degradation does. Surface films, lithium plating, drying electrolyte, they block part of the electrode, so the same reaction has to run through less surface, and its resistance rises. The switch does in one motion what aging does over months, and in a real cell, this change is invisible from the outside. The voltage still looks right, the capacity still looks right. So right now the unit is pushing a small alternating current through the cell and measuring the voltage that comes back. From 800 times a second down to once every 10 seconds. Different frequencies see different parts of the cell. The fast ones pass straight through the surface capacitance, so they only see the metal. The slow ones can't, they're forced through the reaction resistance. So one sweep separates the parts of the cell. An ordinary resistance measurement blends into a single number. So every battery safety system today watches voltage, current, and temperature. Those tell you a cell is in trouble once it's already in trouble. This measurement runs periodically on every cell in the pack on hardware that's already there. So an operator can watch one cell drift away from its neighbors and schedule a replacement instead of reacting to a failure. The value of this diagnostic Nyquist plot is that it gives us 3 different impedances that tell us the impedance changes in the cell over the life of it. We capture these for all 14 cells in the battery every day over the course of a year. That gives us about 1 megabyte of data that tells us exactly what's happening with each cell through the history of the battery. It gives the battery owner an excellent battery passport.
Good. So you've seen the diagnostic process now that we're running. We also have to run a real lab here on site. Our goal is 4 batteries cycling 6 times a day to try and achieve 2,000 cycles a year. It'll all be automated that we run, running the EIS through those batteries, reporting to them, so that we get a set of reference charts so we can see what the natural aging in, if you wish, perfect conditions will be in terms of shifts in the resistance, and that helps us identify the diagnostic parameters for the early advance warning on any of the 15 failure modes. And the benefit of this overall for the customer, we think, is going to be very, very substantial. It's a shift in battery technology. I've got to say, how good's that?